next speaker is Aris Alexandradinata from the University of Illinois. He will talk about distinguishing Dirac metals and giant orbital parameters.
Yeah, thank you. So I'm going to present work that the key experimental player is Mark Chunyu Guo in Philip Moll's group in Lausanne. I'm going to present a smoking gun for Dirac semimetals. We're going to be talking about Dirac Fermons in 3D central symmetric metals. And we're going to look for this type of Dirac nodes, which are fourfold degeneracies, which can occur in points in K-space, in which case are referred to as 3D Dirac metals, and these degeneracies can also occur as lines in K-space, in which case I refer to them as nodal line metals. This smoking gun is from magnetic quantum oscillations alone. In particular, we will not need ab initio band structure calculations or some type of photoemission spectroscopy. Okay, first I have to tell you about the current method of deducing Diracness from quantum oscillations, which is flawed. There's a belief that the pi periphase of a Dirac fermion is in one-to-one correspondence with the pi periphase of with a pi phase offset in the fundamental harmonic of quantum oscillations. So briefly review the single harmonic approximation to the resistivity. Let's focus on the argument here. There's a term proportional to the area enclosed by the cyclotron orbit multiplied by the magnetic length square. There's some phases here which are well known, I will not get into, but the key point is that this is plus minus 1 that people believe is related to the pi periphase. So there's a few problems with this formula. First, that with a spin-orbit coupling, you have spin mixing, and the periphase is not quantized to pi generically. So the second problem is that this pi phase offset may be due to completely different reasons. It may be due to a giant orbital magnetic moment, which is associated to a rotation of a wave packet about its own center of mass. And this is relevant when the spin-orbit energy scale is comparable to the direct interband energy gap, as is true for bismuth, which is a conventional non-topological metal with a G factor of about 100, and this has a pi offset in fundamental harmonic. I'll refer to such metals as giant orbital paramagnets. And of course, the third problem is that higher harmonics can always displace this shift, so can always shift peaks in the resistivity. This formula is not completely accurate, and higher harmonics are always there because Lambda levels are sharp. Okay, so as a result of these problems, there are many controversial claims of Diracness and a general feeling of dissatisfaction in the field. Right, so to recapitulate, if you see a pi phase offset in the fundamental harmonic, it could be due to a Dirac metal, or it could be due to a conventional metal with a giant orbital paramagnetism. I'll refer to the third class of metals as just boring metals. We want a smoking gun for Dirac metals, and I propose an algorithm summarized in 3 steps. First, we're going to rule out boring metals by measuring amplitudes of the higher harmonics in quantum oscillations. Then we're going to distinguish a Dirac metal from an orbital paramagnet by measuring the temperature dependence of the oscillation frequency. And actually, as a bonus, we can obtain from this the Fermi energy of the Dirac fermion. Then we're going to distinguish between Dirac point degeneracies versus line degeneracies by comparing the spin-orbit energy scale with the just extracted Fermi energy. We're going to apply this algorithm to a case study, this intermetallic lanthanum rhodium indium 5, which is a cousin of a heavy fermion superconductor. And we're going to deduce from this algorithm that it has a small Fermi pocket that is Dirac type with a Fermi temperature that's approximately room temperature. But I'm claiming that these steps have wide applicability in a systematic search for spin-orbit coupled topological metals. Okay, so let's consider step 1. We're going to rule out boring metals by considering the higher harmonics. So by higher harmonics, I refer to the harmonics here that enter for R greater than 1. For example, this is the resistivity of lanthanum rhodium indium 5. It has been decomposed into 3 harmonics. I'm going to draw there's some well-known prefactors here which I will not get into, but let me draw your attention to this prefactor, which is cosine R lambda. So this cosine R lambda is due to the interference of oscillations from lambda levels of opposite spin or pseudospin. And lambda that enters in this argument also enters as a subleading correction to the Onsager-Lifshitz quantization rule. And in particular, lambda encodes the Berry phase and the Zeeman coupling to the spin and orbital magnetic moment. Okay. So for boring metals with a weak spin orbit coupling, the value of this lambda is simply given by the free electron G factor and the ratio of the cyclotron mass to the free electron mass. And this simply represents the Zeeman coupling to the spin orbital moment, but not Zeeman coupling to the spin magnetic moment, but not to the orbital magnetic moment. And I should remind you that the cyclotron mass is simply given by the derivative of the area with respect to the energy, and this can be deduced from the temperature dependence of the amplitude of quantum oscillations. Therefore, if we have a candidate metal and we measure lambda somehow, and we find that this candidate lambda differs from the boring value of lambda by a quantity of order pi, then we can deduce that this candidate metal is not boring. Okay, so we need a way to extract lambda for any candidate metal, and to do that, first of all, I should mention for technical reasons, it's not possible to measure the absolute amplitude of a higher harmonic, but what we can do is we can measure relative amplitudes of the higher harmonics. So then we can extract values like cosine 2 lambda over cosine lambda, and if we measure this for the second and third harmonic, algebraically this allows us to uniquely determine lambda. So we can let's analyze this data of lanthanum, rhodium, indium 5. The oscillation frequency is about 7 Tesla, and from the relation of the area to the frequency, we deduce that this Fermi pocket is of the size of order 10 to the minus 4, the total ground zone volume. We also can deduce that the cosine 2 lambda over cosine lambda is minus 1, and so on, from which we deduce that lambda is very close to pi. Furthermore, we can extract the cyclotron mass from the temperature dependence of amplitude, and we find that it's 0.07 the free electron mass. So hypothetically, if lanthanum, rhodium, indium 5 were a boring metal, it would correspond to a value of 0.035 pi, which is much less than the actual lambda we actually measure. So we can deduce from this that lanthanum, rhodium, indium 5 is not boring. Okay, so step 2, we're going to distinguish between a Dirac and this Dirac metal and this giant orbital paramagnets. And the key point is that this type of pockets are distinguished by the derivative of the cyclotron mass with respect to energy. So for a conventional Schrodinger type pocket, the cyclotron mass is constant. But just simply for Dirac pocket, just because the energy is linear in K, we obtain that the derivative of the area with respect to energy is linear in the energy. So it is standard to extract the cyclotron mass at the Fermi level from the Listritz-Kostritz formula, which I presented to you earlier. But this formula holds in a regime where KT is much less than the Fermi energy. So we propose that the derivative of MC with respect to energy enters as a correction to the Listritz-Kostritz formula when KT is not much less than E Fermi. This correction enters in this argument here, and effectively this is a correction to the frequency that is linear that's quadratic in temperature. So here, all these prefactors are known exactly. This is the effective Bohr magneton, and we are proposing to extract essentially the derivative of MC with respect to E from the t-square dependence of the frequency. So let's do that for lanthanum, rhodium, indium 5. This is the frequency plotted as a function of t squared. It's a reasonable linear slope, and from that we can deduce that dE over d log m is 24 MeV. At this point, might we call victory? But then why would we expect this value of 24 MeV? So we need some type of consistency check. So the consistency check I propose is that just from the fact that the energy dispersion is linear, we can deduce that this quantity we just extracted should equal the Fermi energy of the Dirac point. The Fermi energy measured from the Dirac point. Furthermore, the Fermi energy measured from the Dirac point is simply related to the area enclosed by the cyclotron orbit over the effective mass, and that's simply from this linear dispersion. So there's a consistency check we can do here, because the first quantity is obtained from F versus t squared. As I said, area is obtained from the the extrapolation of the oscillation frequency to 0 temperature, and the effective mass is obtained from the temperature dependence of amplitude. So we can measure all these things, and for the measured area of MC, we deduce what we find is a 24 MeV for lanthanum, rhodium, indium 5. Okay. And it is this quantitative consistency between these two quantities that we propose as a smoking gun for Dirac fermion, and thus we deduce that the Fermi pocket of lanthanum, rhodium, indium 5 is Dirac type with a Fermi temperature that is approximately room temperature. Is that 9 minutes? Or? 10. It's my last slide. Okay, so let me just summarize the steps in topofermiology. We want to rule out boring metals by measuring the high harmonics of the oscillation of the quantum oscillations. Then we want to rule out the giant optical paramagnets by measuring the temperature dependence of the oscillation frequency. And as a bonus, we obtain the Fermi energy of the Dirac fermion. And then we can also rule out Dirac node lines in favor of 3D Dirac points if the spin-orbit energy scale is greater or comparable to the Fermi energy. And the reason for this is that Dirac nodal lines are unstable to the spin-orbit interaction, but Dirac points are stable. And from this, we deduce that lanthanum, rhodium, indium 5, the Fermi pocket is definitely Dirac type from step 2, but it also most likely encloses the Dirac point from step 3. So with this, we propose has wide applicability in the systematic search for topological metals. It's especially useful when small Dirac pockets coexist with large Schrodinger type pockets. Thank you.
You want to check it?
Yeah.